Alright, this is Chapter 2, Section 3, Product and Quotient Rules and Higher Order Derivatives. So we're going to start off with the product rule. The product of two differentiable functions, f and g, is itself differentiable. Moreover, the derivative of f times g is the first function times the derivative of the second, plus the second function times the derivative of the first. So it's not as simple as just taking the two derivatives separately and multiplying them together. We have to follow this pattern. So the derivative of f of x times g of x is f of x times g prime of x plus g of x times f prime of x, We can extend that for three functions if we want. We take derivative of the first times the second two unchanged, plus derivative of the second times the first two unchanged, plus derivative of the third times the first two unchanged. So to find the derivative of x squared times sine of x times cosine of x, we're going to look at the three pieces that are multiplied together. We have x squared, we have sine of x, and we have cosine of x. So we start off with derivative of the first. So to get our derivative, f prime of x, we take the derivative of x squared, which is 2x, times the second piece unchanged, so sine of x, times the third piece unchanged, cosine of x, plus, always a plus with our product rule, derivative of the second piece. Derivative of sine is cosine of x, times the first piece unchanged, which is x squared, times the last piece unchanged, which is cosine of x, plus the derivative of the last piece. The derivative of cosine is negative sine of x, times the first piece unchanged, which is x squared, times the second piece unchanged, which is sine of x. Now we do a little simplifying. We get f prime of x equals 2x sine x cosine x plus x squared cosine squared of x minus x squared sine squared of x. And that's where we can leave our derivative. We're going to find the derivative of h of x two different ways. We're going to find it using the product rule, and then we're going to find it by first multiplying. So let's use the product rule. We have two pieces that are multiplied together. To use the product rule, we say h prime of x equals derivative of the first piece. So the derivative of 3x minus 2x squared is 3 minus 4x times the second piece unchanged, which is 5 plus 4x, plus the derivative of the second piece, which is just 4, times the first piece unchanged, which is 3x minus 2x squared. Now we simplify this a bit. We're going to FOIL over here. We get 15 plus 12x minus 20x minus 16x squared. Distribute my 4, I get plus 12x minus 8x squared. And combine my like terms, I get negative 24x squared plus 4x plus 15. So my derivative of h of x is negative 24x squared plus 4x plus 15. Then we're going to do this problem by first multiplying it out. So we're going to take h of x and we're going to FOIL. So I'm not doing the derivative yet. I take 3x times 5, which is 15x. 3x times 4x is 12x squared. Negative 2x squared times 5 is negative 10x squared. And negative 2x squared times 4x is negative 8x cubed. So h of x, before doing anything with the derivative, is negative 8x cubed plus 2x squared plus 15x. Now I take my derivative using just my power rules. Bring down the 3, so I get negative 24, subtract 1 from the power, x squared. Bring down my 2, I get 4, subtract 1 from the power, I just have x. And the derivative of 15x is 15. Oh, look at that. I got the same derivative either way. It just depends where you feel like multiplying. All right, for our next one, this one we absolutely have to use the product rule. There's no way for me to split it apart, so I don't have to. My first piece is going to be 3x squared. My second piece is going to be sine of x. So for my derivative, dy dx, I take the derivative of 3x squared, which is 6x, times the second piece unchanged, which is just sine of x, plus the derivative of sine, which is cosine of x, times the first piece unchanged, so 3x squared. I'm just going to clean that up a little bit. dy dx equals 6x sine of x plus 3x squared cosine of x. And that is all we can do. That is my derivative. All right, let's find the derivative of 2x cosine of x minus 2 sine of x. To do this one, we have to do the product rule for only part of it. We have to use the product rule on this first piece because I have 2x times cosine of x. The 2 sine of x doesn't have to use the product rule, and we can just do that derivative straightforward. So dy dx equals the derivative of 2x is 2 times cosine of x unchanged, plus my 2x will stay, times the derivative of cosine, which is negative sine of x, minus the derivative of 2 sine of x, which is 2 cosine of x. Well, now I can combine some like terms. 2 cosine of x and negative 2 cosine of x cancel each other out. I'm left with negative 2x sine of x as my derivative. All right, so we're going to keep going here into the quotient rule. The quotient rule is if I'm dividing two functions. The function f divided by g of two differentiable functions, f and g, is also differentiable at all values of x as long as the denominator is not 0. Moreover, the derivative of f over g is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. In math terms, the derivative of f of x over g of x is f prime of x times g of x unchanged minus g prime of x times f of x unchanged, all over g of x squared. So that's the derivative of the top times the bottom unchanged minus derivative of the bottom times the top unchanged, all over the bottom squared. Let's dive right in. We are going to find the derivative of 5x minus 2 over x squared plus 1. To find this derivative, we go dy dx equals, we take derivative of the top. Well, the derivative of 5x minus 2 is 5, times the bottom unchanged, x squared plus 1, minus, so quotient rule, we always use a minus, derivative of the bottom, the derivative of x squared plus 1 is 2x, times the top unchanged, which is 5x minus 2, all over the bottom squared. We do need to simplify this a little bit. We're going to distribute in the numerator and see if there's any like terms we can combine. We get 5x squared plus 5 minus 10x squared plus 4x. You do not need to worry about multiplying out that denominator. You can leave it as x squared plus 1 squared. And when we do this, we get negative 5x squared plus 4x plus 5 all over x squared plus 1 squared. It is important to note what the denominator can't be. So if there was anything that would make the denominator 0, we'd have to say x can't equal that. But there's nothing in this case, so we are done. Our next example, we are going to find the equation of a tangent line at negative 1, 1 of the function f of x equals 3 minus 1 over x plus 5. Now this is a wonky looking function because we have a fraction within a fraction. The hint is to rewrite it before differentiating. 1 over x is the same thing as saying 3 minus x to the negative first power. So that makes my life a lot easier for finding my derivative. So my derivative, and sorry, anytime we're finding a tangent line, we want to find the slope at that point. We find the slope using the derivative. So the derivative of the top, the derivative of 3 minus x to the negative first power. Well, we get positive x to the negative second power times the denominator unchanged, minus the derivative of the denominator is 1 times the top unchanged, all over the denominator squared. Now this is one problem where I do not recommend simplifying it because I have to plug in this point So I don't need to bother simplifying. I'm going to have to simplify when I plug in the number anyway. Notice that my derivative only has x's in it, so I only need to plug in the -1. So we're finding f prime of -1. So I have -1 to the -2nd power times -1 plus 5 minus 1 times 3 minus -1 to the -1st power all over -1 plus 5 squared. Well, that makes +1 times 4 minus 1 times 3 plus 1 all over 4 squared. So my slope is 4 minus 4 over 4 squared. My slope is 0. All right, that's only half the problem. I need to find the equation of the tangent line. So I need the equation of a line with a slope of 0 that goes through the point -1, 1. So I do y minus y1 equals my slope times x minus x1. Distribute, I get y minus 1 equals 0. Add that 1 over. The tangent line is horizontal. It is y equals 1. All right, so we're going to find some derivatives. And our hint here is to use the constant multiple rule. So basically, we are going to rewrite these before we take the derivative. Because x squared plus 3x over 6 can be rewritten as 1/6 x squared plus 3/6 or 1/2 x. And now my life is much easier. I do not need to use the quotient rule. You only have to use the quotient rule if you have x's in the top and the bottom. So I bring down my 2, dy dx equals, well, 2 times the 6th is 1/3. Subtract 1 from my power, I get x. The derivative of 1/2 x is just 1/2, so there's my derivative. For y equals 5x to the 4th power over 8, really that's 5/8 x to the 4th power. So to get my derivative, dy dx, bring down the 4. Well, 5/8 times 4 is 5 over 2. And subtract 1 from my power, I get x cubed. And now c looks a little wonkier. First thing we'll want to do on c is distribute the -3. So we get -9x plus 6x squared over 7x. But now we can simplify this again because -9x over 7x is -9/7. And 6x squared over 7x is 6/7 x. And now my derivative, dy dx, is very simple because the derivative of -9/7 is 0, and the derivative of 6/7 x is just 6 over 7. And finally, for part D, when I rewrite this one, I want to call it 9/5 times x to the -2nd power, since my x is in the denominator. Well, to get my derivative, dy dx, I bring down my -2nd power, so I get -18 over 5. And I subtract 1 from the power, making it a -3. Now, we don't like to leave negative exponents usually, so we're going to drop it into the denominator. 5x to the +3rd power. So -18 over 5x cubed. All right, now for some derivatives of all of the trig functions. We already have sine and cosine. The derivative of tangent is secant squared of x. The derivative of secant is secant of x tangent of x. The derivative of cotangent is negative cosecant squared of x. And the derivative of cosecant of x is negative cosecant x cotangent x. We could prove all of this using the quotient rule if I turned everything into sines and cosines. We are not going to spend the time doing that today. So let's find some derivatives. The derivative of x minus tangent of x. Well, I'll call it dy dx. The derivative of x is 1, minus the derivative of tangent of x is secant squared of x. There's my derivative. For the derivative of x secant of x, we have to use the product rule because we have two things multiplied. So dy dx equals the derivative of x is 1 times the second part unchanged plus the first part unchanged, so x, times the derivative of secant, which is secant x tangent x. So there's our derivative. All right, we're going to find this derivative in two separate ways. We're going to show that both of those ways work and give me the same answer. So the first way I see division. I'm going to find it using the quotient rule. So dy dx, derivative of the top, the derivative of 1 minus cosine of x is positive sine of x, times the bottom unchanged, minus the derivative of the bottom, which would be cosine of x, times the top unchanged, all over the bottom squared. Well, when we simplify this, we get sine squared of x minus cosine of x plus cosine squared of x, all over sine squared of x. And if we remember our simplification rules, sine squared plus cosine squared is 1. We get 1 minus the cosine of x over sine squared of x. There's our derivative. If we need to, we'll work with that further in a minute. The other way we could find this derivative is if I say, okay, well, 1 over sine is cosecant, and cosine over sine is cotangent. Well, I know dy dx, the derivative of cosecant is negative cosecant cotangent, minus the derivative of cotangent is negative, so plus cosecant squared. I have two different derivatives. We're going to see if we can make those equal to prove that this actually works. So let's simplify this side because I think it'll be easier to change everything into sines and cosines. So negative cosecant is 1 over sine. Cotangent is cosine over sine. Plus cosecant squared would be cosine squared over sine squared. And when I combine this, I get negative cosine of x over sine squared of x plus cosine squared of x over sine squared of x. Just kidding, I made a mistake. Cosecant squared is actually just 1 over sine squared of x. What am I doing here? 1 over sine squared of x. Okay. So now when I add these two fractions together, I get negative cosine plus 1, or 1 minus cosine of x, all over sine squared of x. And look at that. They're exactly the same. Either way works out just fine. So this is just a quick note about how much work happens after taking the derivative. In our first example, we took the derivative and got that. Then we had to do all the work to simplify it. This example, we take the derivative real quick, but then we do all the work to simplify it. We do a bunch of work in the simplification process. The derivatives aren't usually the hard part. It's the simplification that people run into their mistakes on. And the last new topic for today is higher order derivatives. First up is acceleration. Acceleration is the derivative of the velocity function, or the second derivative of the position function. So if I take my position function and find the derivative, I get the velocity function. But if I take my velocity function, and take the derivative, why does it make you v prime of t, I get my acceleration function. So the acceleration function is two derivatives of the position function. A second derivative is just the derivative of the derivative. We denote it with a double prime. A higher order derivative is a second or higher derivative of a function. It must be a positive integer order. I can take the third derivative, fourth derivative, but I cannot take the 2.5 derivative. Third derivative would be the derivative of the second derivative. We can denote it with a triple prime. And some notation here. If I can get this to show nice, there we go. In my first derivative, I have y prime or f prime of x or dy dx or the derivative of f of x, or you can use this notation that we rarely use. Second derivative, we use a double prime, or notice it's d2y dx2. We put the 2's in wonky places, so be careful with that. Third derivative, 3 tick marks, or d3y dx3. Fourth derivative, we stop using tick marks, we start just putting in a 4. And higher than that, we start just using the number instead of having to count all those little tick marks. So, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these objects is given by this S of t function, where S of t is the height in meters and t is the time in seconds. We need to find the ratio of Earth's gravitational force to the moon's. We're finding the ratio of acceleration on the moon to acceleration on Earth. Well, acceleration on the moon, S prime of t, is going to be, bring down the 2, I get negative 1.62 t. And S double prime of t, which gives me the acceleration, is just negative 1.62. On Earth, acceleration due to gravity, so the second derivative of the position function, is negative 9.8 meters per second. So I want the ratio of Earth's gravitational force to the moon's. It is negative 9.8 over negative 1.62. So the ratio is about 6.049 to 1. The Earth's acceleration due to gravity is about 6 times the acceleration, well, there's no gravity on the moon, so the acceleration that happens on the moon. So now you'll practice.